All right, so before we start our next section on page 139, are there any homework questions you guys want to go over? I know we finished a section yesterday about synthetic division and 2 important theorems. I was just going to offer if you wanted to go over any question you might have.
Good morning.
Good morning. Anything for the office today? I think we're good.
Okay.
Thank you.
Bye.
Bye. Homework going once. Going twice. No. Question? This is the next section. Sorry, no. This is the next section. If there are homework questions, I'll bring up those pages. No, you're right to have that perplexed look on your face because we're going to talk about this today. All right, let's go ahead and take a look at page 139. So we're going to continue to look at graphs of polynomials. We're going to continue to look at their x-intercepts or zeros, okay, where they touch or cross the x-axis. What we're specifically going to look at today, what I think is a really neat idea, which is kind of based off the graph itself. If you can identify how the graph is touching or crossing the x-axis, you can actually figure out the equation of the graph. I think that's kind of interesting. Just by looking at it, you can figure out the equation. But you have to kind of know what to look for. So that's what we're going to talk about today. So on page 139, we have these 3 graphs. We have a cubic function, a quartic, and a quintic. So in terms of polynomials, cubic is an x to the 3rd power. Sometimes we call that power a degree. You might hear that word pop up a few times because notice how the power of 3 is kind of written in a degree spot. If you were to think about 70 degrees, the little circle would be in the top right hand side. A quartic is an x to the 4th and a quintic is an x to the 5th. We're already familiar with cubic equations, okay, those kind of S-curve type shapes. But notice how when you get into higher powers or higher degrees, the curves kind of start to increase. You see how you get more of them? So a kind of neat way to determine, just looking at a graph, if it's cubic, quartic, or quintic, is to count the number of curves you have. Notice how in this one we have 2 curves. In this one we have 3. And in this one we have 4. So what do you think the connection is between the number of curves and the type of equation? Yeah. Right, the number of curves you have is 1 less than the power. Okay. This quartic example, though, is a little tricky because I know that these, or at least this section right here, doesn't look like a curve. But do you notice how if you were to draw it, your pencil would kind of change the way it's being traced? I know it's a little tricky because it's not one of those clear-cut curves, okay? But there is some type of change in curve there, and we're going to talk about that today. All right, so cubic, quartic, quintic. We have those 3 different types of polynomials. Maybe we'll go ahead and write this down. We have 2 curves, 3 curves, 4 curves. So that's one thing we can identify based off the graph to help us determine what type of polynomial we have. Cubic, quintic, quartic, those ideas. All right, some other characteristics we can identify specifically in the next 2 rows are what are called end behavior. So I don't want you to overthink these. Like if you literally were to say the phrase end behavior, what we're going to try to figure out is what is the graph doing on the ends of the graph. Okay, not necessarily in the middle, kind of towards the origin. So if you were to trace this cubic graph to the left, how would you describe what the graph is doing? Yeah. It's descending, it's going down, it's negative, something like that, okay? So in terms of like mathematical notation or phrasing, we're going to say as x approaches negative infinity. Remember how we kind of had that notation for continuity? As x approaches 2 from the right, as x approaches 2 from the left. Kind of the same idea, but this time we're approaching the ends of the graph. So we're either going towards a positive infinity or negative infinity. So as the x values get smaller and smaller, okay, aka we're traveling to the left, the graph, okay, meaning f of x, whatever name it might be, also approaches negative infinity. Okay, it's going down. Remember, f of x and y are kind of the same idea. So as the x's go to the left, the y's go down. We're describing the end behavior, what's happening on this side of the graph. Okay, let's try to write a similar statement for the right end behavior. So if you were to trace the graph to the right, the x values are getting larger, okay, because you're traveling to the right. So what are the y values or f of x values, whatever variable you want to say, what are they doing? If you were to trace it with your pencil, are we thinking they're going up? All right, I see pencils moving, which means you're writing something down. Okay. It'd just be up or positive infinity, okay? Does that make sense? What's going on the left, what's going on the right? We're just determining if it goes up or down, basically. Okay? Because we're eventually going to draw a connection between end behavior and what type of graph we have. Yeah?
So for left end behavior, you have to say like as the graph approaches negative behavior and then y for the right end behavior?
Well, you could say f of x here. Is that what you mean? Like why you use it? You can use f of x or y. They both mean the same thing. So whatever you feel comfortable using, that's fine. Okay? But what is important is left end behavior, your x's should always be approaching negative infinity, whereas for right end behavior, they should be always approaching positive infinity. Okay? Because this is signifying left and this is signifying right. All right? Let's go ahead and identify the zeros, aka the x-intercepts. Can you figure out those locations based off the graph where you touch or cross the x-axis? Go ahead, Rebecca.
-2, -1, 1.
Looks good. Okay, so we did a few graphical characteristic analysis for the cubic. Okay, let's go ahead and do the same thing for the quartic and the quintic. Do you guys think you can try those on your own? Want to give them a shot? Did I miss it?
You just put -3, I think you miscounted.
Oh, yeah. Thank you. Other than that, are we good? Perfect. Okay. So what we're going to do, we're eventually going to talk about end behavior a little bit more. We're going to save that for the next section. But what we're going to focus on in this section specifically are these x-intercepts. So if you take a quick moment, okay, and if you were to actually physically look at the graph at these spots, okay, all these x-intercepts, notice how the x-intercepts are kind of different in some cases. Notice how the x-intercept at this point is different than the x-intercept at this one. Do you notice how the graph looks a little different around that spot? Do you see how at this one the graph kind of goes straight through it, like it strikes through that point? Whereas here it kind of levels off at that point. Whereas at this one, it's not even going through the x-axis, it's just touching it. Do you see those three different types of x-intercepts we can have? So those different types are actually signifying what the equation of these polynomials looks like, and that's what we're going to talk about. So we kind of have three different types of x-intercepts, and we're going to classify them in this section. Okay, so the particular vocabulary term for this concept is what's referred to as multiplicity. Okay, if you think about multiplicity, you can see the word kind of multiple in there. So what we're going to do is we're going to define this term multiplicity as the number of times a zero, aka x-intercept, is a factor of a polynomial. We kind of looked at this concept yesterday. It was the very last example we did where we had to do synthetic division after synthetic division after synthetic division. Remember that one? We kept looking for a remainder of 0. We were actually identifying multiplicity and you didn't know it just yet. Okay, but we're going to do more of that today. So what we're technically looking here for is how many multiples or how many times does a 0 or a factor show up. So I want you to take a quick second and read these three statements at the bottom of the page. We're going to draw a connection between the type of x-intercept we have and the multiplicity it has. How many times is it a factor? All right, did we read those three statements? Okay. Now, on the board, you can't see the statements, but I want to make sure we can see the graphs. Okay. So the first statement says, in the graph of f of x, okay, that's our first one, all of the zeros have a multiplicity of 1. So I'm just going to go ahead and label that multiplicity here, just as a reference. The second statement says, in g of x, the negative 2.5 has a multiplicity of 1. Whereas the x-intercept of 2 has a multiplicity of 3. Okay, it's a factor 3 times. And then the last statement for h of x, negative 4, negative 2, and 5 all have a multiplicity of 1, whereas 2 has a multiplicity of 2. So based off of those three statements, can you draw a connection between the type of multiplicity we have, how many times is it a factor, and what the graph looks like at that x-intercept? Can you find a pattern? What do you think, Rebecca?
If it has a multiplicity of 1, it goes straight through it.
Yep.
If it has a multiplicity of 2, it just kind of touches it.
Yep.
If it has like 3, it kind of levels.
Levels. Perfect. Okay, do we see that connection? All of the multiplicities of 1 go straight through the x-axis. It's like you're drawing a straight line, kind of.
Excuse the interruption. Attention teachers and students. The high school is currently undergoing a drill. All students and staff are to remain in the classrooms. Shut your doors and remain in the classrooms. Teaching can continue. You will be notified when this drill has concluded. Again, we are undergoing a drill. All students and staff are to remain in the classrooms with the doors shut. Teaching can continue. We will notify you when this drill has concluded. Thank you.
Well, it's not like we're all curious now, right? All right, so let's go ahead and we're going to write down this connection, this relationship on the back page, okay? So I didn't want you to have to do a lot of flipping or anything like that, but we're going to go ahead and write those down in these little boxes, okay? So describe the behavior of the graph as it approaches a zero whose multiplicity is 1, okay? On the previous page, we said that the graph strictly goes through the x-axis at that spot. It kind of just strikes through it. There's no curvature change. Okay, it's just like you're drawing a line through the graph, or through the x-axis rather. So we'll say the graph crosses the x-axis. Maybe you want to say strikes through. All right, the second, or the third block rather, is asking us, what does the graph look like when an x-intercept has a multiplicity of 2? Okay, if you need to flip the page, we said, or Rebecca said rather, that the graph kind of just touches the x-axis at that spot. It kind of bounces. You have a hump going on. So we'll say the graph just touches the x-axis. There's actually a mathematical term that we use instead of saying just touches. I'm not sure if you've heard this term before or not. It's what's referred to as tangent. Okay, that definitely shows up like in a geometry sense. Whenever you guys were talking about circles and chords and lines and all of that, a tangent line technically just touches a circle at one spot. So we can kind of say that here. The graph just touches the x-axis. You might see that word tangent pop up sometimes. I just want you to know that's what it means. Okay, it just touches. Describe the behavior of the graph as it approaches a multiplicity of 3. Okay, so we said, or Rebecca said rather, that the graph crosses the x-axis but is level. Okay, it doesn't strike through it like a line. Okay, you do go through it, but it's almost like a level spot. Do those make sense based off the graphs we looked at? Okay, so we're going to utilize those connections. The first one at the top, though, says, what do you notice about the sum of the multiplicities? So if you were to add up all of those individual multiplicities, how does that relate to the degree or the power of the function? So if I go ahead and reference back here, if we were to add up all of these multiplicities, what would we have? If we were to add up these, what would we have? If we were to add up all of those, what would we have? What do you notice about the sum of the multiplicities related to the type of function we have? Yeah?
It matches the degree.
It matches the degree. 1 plus 1 plus 1 is 3. 3 and 1 gives us 4. 2 and 3 give us 5. Okay? So if you were to add up all of those individual multiplicities, it's basically telling you what type of polynomial you have. Cubic, quartic, quintic. Okay? So we'll say the sum of the multiplicities is the same as the degree or power, exponent, whatever word you want to use. Are we okay with those connections, those characteristics? Those make sense based off of the examples? okay? All right, so let's take a look at this multiplicity idea a little bit further. Okay, how many times does a factor show up? So in these next examples, we have an equation, we have its graph. It's going to ask us to focus on a specific x-intercept, okay, a specific spot. So in this case, we're going to look at the factor x plus 1. If that is the factor, what is the 0 or x-intercept or root? Okay, that's another synonym. They all kind of mean the same thing. Where's the x-intercept based off of that factor? Yeah. -1. Okay, so graphically speaking, we're focusing on this spot right there. Okay. What we're going to do is we're going to use synthetic division to determine how many times this factor shows up or is a factor of this polynomial. We're basically determining the multiplicity. Now, we could probably determine what the multiplicity is based off the graph, right? Because we talked about the different connections. But let's say we didn't have the graph. Okay, we just had the equation. How could we determine the multiplicity? So let's go through our synthetic division. Okay, well, -1's our little box number. We'll go ahead and use the coefficients from the polynomial. Are we okay with that division? Did I miss something? I saw the hands, yeah.
How'd you do the -1 times?
Oh my gosh, okay. So this would be -1, -2, 2, I don't know. That's better. It's funny that this is going on right now because apparently last night my mind was not where it was supposed to be and my husband was bringing up how I have pregnancy brain lately, and this is just like reaffirming his observation. I'm sorry. Is that better though? Yeah, okay. So we know x plus 1 is a factor at least once, right? Because the remainder is 0. Let's try it again. Okay, see if it's a factor again. We're going to take the quotient coefficients and use those in the synthetic division. Is it a factor again? No. All right, so notice how this factor only is a factor once. Okay, it only goes in evenly once. So we would classify its multiplicity as 1. Okay, how many times a 0 or an x-intercept is a factor? In this case, it's only once. So based off of that idea, describe the behavior of the graph at this root, x-intercept, 0, whatever you want to say. So based off the connection that we did from the boxes at the top, what should the graph look like? Again, pretend you didn't have it, because you can kind of cheat, it's there, but what should it look like? Yeah? Straight through the x-axis. Okay, so we'll say at the x location of -1, the graph goes straight through the x-axis. Now you can reference the graph and notice how that's the case, okay? If you were to draw a line straight through, that's kind of what's happening around that x-intercept spot. Okay, so based off the multiplicity, we can determine what the graph looks like at that location. All right, let's try the next one. Again, pretend the graph wasn't there, at least for now, because we'll go ahead and use it to double check our work. We're going to focus on the factor of x minus 1, which means the x-intercept would be +1. Let's go ahead and see how many times this x minus 1 factor is a factor. How many times does it go in evenly? So we'll test our synthetic division. Based off the synthetic division, what would we describe as the multiplicity? How many times is it a factor? Yeah. 2. All right. So without looking at the graph, okay, don't cheat just yet. Describe the behavior of the graph. Okay, so based off those connections at the top of the page, what should the graph look like at this x-intercept? Yeah.
The graph just touches the x-axis.
The graph just touches, okay, or you can say is tangent, okay, that vocabulary term if you want to use that. The graph just touches the x-axis at the x-intercept of 1. So if you were to reference the graph, notice how that's checking out. Okay, we kind of touch at 1 and then we bounce back. Okay, we're just touching it at that spot. So far so good? All right, let's try the next one. All right, don't look at the graph just yet. We're looking at the factor x minus 1. So our root 0 x-intercept would be positive 1. Let's go ahead and see how many times it's a factor. How many times does it go in evenly? So we're going to have some division to do. So based off those divisions, what would you describe as the multiplicity? Yeah, 3. All right, so without looking at the graph just yet, what does the graph look like at that x-intercept? Can we describe it based off of that multiplicity that we know? Yeah?
The graph levels off at the x-axis.
The graph is level at the x-intercept. However you want to phrase it is fine. The graph is level at the x-intercept of 1. Okay, so it is going to go through the graph, but it goes through in a level type path. So notice how if you did check the graph, it is kind of level there. It doesn't strike through it like the other one does. It levels off. We doing okay? Everything checking out? All right, so I know it's not part of the directions exactly, but what we can do is actually write the equations of these polynomials in factored form based off of these multiplicities. So notice how in all these examples they gave us standard form at the top. Okay, let's go ahead and we're going to try to rewrite the equation in factored form. Okay, so it's all based off of the x-intercepts as well as the multiplicities, okay, how many times it shows up. So if you were to take a look at this first graph we did here, we can identify the x-intercepts. They look like -2, -1, +1. And if those are the x-intercepts, what do the related factors look like? Let's see, if we have an x-intercept of -2, what would the related factor have to look like? We need an x plus 2, I heard it, good. Okay, another x-intercept of -1 would need an x plus 1. And the last x-intercept of +1 would need a -1. Okay, so we can identify the factors, but then we can go back and identify the multiplicities. How many times do they actually show up? And if we were to analyze the graph at these spots, notice how they all strike through the x-axis. So all of these factors only show up once. Okay, it's not like we have to write it again. Okay, so they only show up once. So this is what the factored form would look like of this polynomial. No factoring needed. Okay, you could go through grouping if you wanted to and you'd still get the same result. But if we have a graph, we can just look at the x-intercepts and then determine the multiplicities to help us write those factors. It's kind of a quick way to factor when you have a graph. All right, let's try our next one. So looking at the x-intercepts, it looks like perhaps -1.5, we'll say, as a fraction. That's -3/2. But it would have to be positive, right? Because if it's negative as an x-intercept, we would need the opposite as a factor. And then the other x-intercept we have is 1, so we would need a factor of x minus 1. Yeah?
Well, the first one is the derivative is 2x plus 3.
Exactly. Do you notice how this kind of looks like a divide and slide type deal? Okay? You could slide the 2 out front. So if you wanted to write this as 2x plus 3, you could. But technically they mean the same thing. Okay? So based off of the x-intercepts, these are the factors, but we have to determine the multiplicities. How many times do each of these factors show up? Okay, how many times do they go in evenly? So if we look at this x-intercept, if it strikes through, we know it only shows up once. However, at this x-intercept, since we're just touching it or we're bouncing, it shows up twice. The multiplicity is 2. So right now, you only have it written once there. How do you want to symbolize or show that it shows up twice? Yeah. Square it. Good. Because if you had to write another x minus 1, wouldn't you have x minus 1 times another x minus 1? You could technically write that twice. So in factored form, the multiplicity is actually showing up as the power on the factors. Notice how all of these technically have a power of 1, right? We just don't write it. Same thing going on here. Okay, so the multiplicity is the power when you're looking at factored form. Okay, let's try the last one we just did here. Okay, this was a crazy standard form. You had 5 terms. So we never really talked about how to factor a polynomial with 5 terms. At most we did was 4, right? Because we would have to do grouping. So factoring this is going to be kind of a bear or a pain. But if we have a graph, maybe we can analyze the x-intercepts and therefore the multiplicities to see what the factors would look like. So based off of this graph, an x-intercept of -2, we would need an x plus 2. Based off of the 1, we would need an x minus 1. So those are the factors. but then we have to go back and analyze the multiplicities. How many times do they show up? How many times are they a factor? So since we strike through at -2, that multiplicity is 1. And since we are level at +1, that multiplicity is 3. We just factored this equation without really needing to do any factoring techniques. It's kind of quick, isn't it? Okay. Notice again how if you were to add the multiplicities together, 1 plus 3 would give us 4, and that is the power of your standard form equation, right? That was another connection we realized before. Okay, so it's all coming together. We doing okay? Perfect. Okay, so what we're going to do, we're going to stop there for today because this is kind of a good, I guess, a place to stop, because we're going to talk about something a little bit different with the zeros in the rest of the section. So I don't want to start that and then come back to it after your long, envious weekend. Okay, so we'll stop there for today. In terms of your homework, though, you could probably do the top page. Notice how that block looks very similar to what we did today. You could probably even do the bottom one too. Okay, so maybe you can go ahead and try some of the homework questions from this section in the remaining time we have left.